So what we're going to be looking at today are the multiple choice questions of the OCR Physics A Exploring Physics from 2018. So let's get started. The first question over here, it says which electrical quantity has the SI units amp seconds? Well, remember charge, so let's try again. Charge Q is equal to I multiplied by T, one of the basic charge formulas. We know that the current A, that's in amps, and we know that the time is in seconds. So the correct answer would be A, charge. Let's not forget to write that in. Okay, right, the second one, 3 resistors are connected in a circuit, and you have each of the values of the resistances. What is the total resistance of the circuit? Okay, well, we have a mixture of series and parallel resistors, so those two guys here are connected in parallel, and on top of that we're going to need to add the one which is 20. So the total resistance in this circuit, let's say that R, we call it R total, is going to be 20 plus. Now if they're in parallel, we don't just add them, but we have to use the 1 over rule. So the total resistance for the circled in part of the circuit is going to be 1 over 10 plus 1 over 10, and then 1 over that, which we can represent by to the power of minus 1. So if we put that in a calculator, or if we just quickly calculate it, it will be 25 ohms. So the correct answer is C. Okay guys, question number 3. An electron has a de Broglie wavelength equal to the wavelength of the X-ray. Now a good thing to remember that an X-ray will vary anywhere between sort of 10 to the power of minus 9 meters to about 10 to the power of minus 11 meters. So let's just take an average value of about 10 to the power of minus 10. So let's say that this is an estimate question, so we don't need to be absolutely precise, but somewhere around 10 to the power of minus 10. What is the best estimate of the momentum of the electron? Okay, well, for this one we have to use the following equation, that the wavelength of an electron is given by h over p, where h is Planck's constant. Now just simply rearranging for the momentum will be Planck's constant divided by the wavelength, so this is going to equal to 6.63 times 10 to the power of minus 34 divided by 10 to the power of minus 10. And if we put that into a calculator, well, or we can just calculate that, really that will just be about 6.63 multiplied by 10 to the power of minus 24. Now looking at those answers, the closest answer to this one is C. So 6.63 times 10 to the power of minus 24 kilogram meters per second. Okay, next one, question number 4. A vibrating tuning fork is held above the open end of a long vertical tube. This is a really fun experiment. If you haven't done this, I really recommend. You can definitely showcase how a sound stationary wave can be formed. But anyhow, so I digress. Let's go back to the question. The other end of the tube, which is also open, is immersed in a tank of water. You can vary the length of the column. The wavelength of sound from the vibrating tuning fork is 150 centimeters. So the wavelength, I'm just going to write that down on the side, is equal to 150 centimeters. What length of air of column will not produce a stationary wave? Okay, well, the first thing to remember is that if we have a standard stationary wave with a node and an antinode and a node, etc. In fact, shall we just draw a little stationary wave here? So if we have something like that, let's say this could be sort of our second harmonic on a piece of string or something like that. We have a node, an antinode, a node, an antinode over here, and that's a node as well. And with the same amplitude, you have this piece of string vibrating. Now the distance between a node and an antinode is 1/4 of a wavelength. So this distance from here to here, that's equal to 1/4 of a wavelength. That's really important for this question over here. whenever we have a closed or an open pipe, what is known as our boundary conditions change. So over here we have a sort of fixed boundary. So this it will always be a node. So always a node. Now, if you want to have a stationary waveform though, with a sound wave for a musical instrument, we are going to want to have an antinode on the other end. So just over here we have to have an antinode. Now that means that certain harmonics are just not allowed. For example, our standard normal second harmonic, which would have a node on one end and a node on the other. So if our length of the instrument, let's just say if our length was equal to let's say half a wavelength. So if our length is equal to half a wavelength, which is in this case is 75 centimeters, what we're going to get is a node on one end, which is fine. That's the fixed point over here. But we're also going to get a node onto the open end of the pipe as well. Now you cannot form a stationary wave. Additionally, there's not going to be any displacement around around that end as well. So this is totally not allowed, I'm afraid. So in this case, which length of air column will not produce a stationary wave within the tube? The correct answer will be B. Okay guys, question 5. 3 identical resistors X, Y, and Z are connected to a power supply. So let's give it some resistance values. So I'm going to call this one R, and this one here will have a resistance R. This one here will also have a resistance R. The power dissipated in resistor Z is 24 watts. What is the power dissipated in resistor Y? Okay, well, if you remember, because this is a parallel circuit, the potential difference will remain constant across each branch of the potential of the parallel circuit. So for example, let's say that the potential difference across Z is V, then the potential difference across X plus Y will also be V. However, that means that individually these guys over here are going to have half of that resistance. So across X the voltage will be V over 2, and across Y the voltage will be V over 2 as well. Now, how does power depend on voltage and resistance? There's an equation in your formula sheet which says that P is V squared over R. Additionally, you could quite quickly derive this. If you can't quite remember this, you should remember that P is equal to V times I, and because I is equal to V over R, this turns into V times V over R, which is equal to V squared over R. So this is where this equation comes from, if you have forgotten. Okay, well, now in this case, the resistance, that's the same across all 3 of those resistors. But what happened, how does the voltage across Z, which is just V because there's just one component in the circuit, how does that compare to the resistance across Y? Well, V squared is decreased by, so this one decreases by a half squared. Yeah, so it actually decreases 4 times. So in other words, the power should decrease 4 times as well. Yeah. So our original power is 24. So divide that by 4. If it decreases 4 times, because we're multiplying both sides of the equation by a factor of a half squared, this should give us 6 watts. So the correct answer is A. Which is the best value for the elementary charge E in terms of both accuracy and precision? So that's question 6. Okay, well, as given in our formula booklets, the elementary charge is 1.6 multiplied by 10 to the power of minus 19, and we have quite a lot of absolute uncertainties. So this one over here, 1.5 plus or minus 0.5, that actually varies between 1 and 2 times 10 to the power of minus 19. So it's not going to be this one. the one after that, b, that varies between 1.9 and 1.1 times 10 to the power of minus 19. So that's quite a high range. C, 1.7 plus or minus 0.2 times 10 to the power of minus 19, and D, 1.8 plus or minus 0.2 times 10 to the power of minus 19. Out of the two remaining options, C is by far closest to the real value, and it's both more accurate, and because it's closer to the real value, and it's more precise as well because there's a smaller absolute uncertainty. So the correct answer is C. Question 7. The amplitude of a sound is 12 micrometers at a distance of 1.5 meters from a loudspeaker. What is the amplitude of the sound? 4.5 meters from the loudspeaker. Okay, well, we need to remember a couple of equations over here. The first one is that intensity tends to be proportional to the square of the amplitude of a wave. Additionally, we know how a wave, the intensity of a wave depends on the distance by the following equation: I is equal to the power divided by 4 pi r squared, which is the surface area of a sphere. We can combine those two equations and we can get a relationship between the distance, which in this case is r, because you can always assume that you're at the end of an imaginary sphere, really, and the amplitude, a squared. So P over 4 pi r squared is equal to K a squared. Now the two quantities which are really important in this case are a squared and r squared. Notice the pattern here. That's the next step. So when you go from 1.5 to 4.5 meters, what you're doing is you are multiplying the distance by a factor of 3. So the distance increases by a factor of 3. Notice though that the distance is inversely proportional. I'll just do that in a different color just to make it absolutely clear. But so r increases by a factor of 3. Now when that happens, the amplitude has to decrease by a factor of 3 because they're inversely proportional. So if A was 12 micrometers before, if you increase the distance by a factor of 3, then A must decrease by a factor of 3. So that the correct answer will be 12 over 3, which is 4. So B, 4. There are quite a few different ways of tackling this problem, but I thought this is probably by far the easiest because ultimately this is a 1-marker question. Of course you can plug in some values, then you can cancel out P, you can cancel out the 4 pi's, work out the constant K, etc, and then do some calculations and you're going to come up with exactly the same answer. However, this was the logic that I would employ if I was in an exam situation. So hopefully this makes sense. If not, feel free to drop a comment, guys. Question 8. An isolated metal sphere is charged using a power supply. Which single quantity can be used to determine the capacitance of the sphere? Now, if we look into your formula sheet, you're going to find a formula for the capacitance of a sphere. It doesn't explicitly tell you that it's the capacitance of a sphere, but the formula is that C is equal to 4 pi epsilon naught R. Now, there's a little bit of a trick to this question. This R over here is really easily confused with resistance, but in fact that's the radius of the sphere. So that's really important. That's the radius of the sphere. So the capacitance of a sphere can be determined only by knowing its radius or diameter, which is the radius of over 2, which is absolutely fascinating. In other words, if you give me a radius or a diameter, I can tell you the capacitance of the sphere. Please note that this equation only applies for a spherical shape though. So in this case, the correct answer is A. Moving on to question number 9. A capacitor is charged through a resistor. So that's really important. This is a charging problem because the maths of capacitors is a bit different when we're dealing with charging compared to discharging. The cell has an EMF of 1.5 volts and no internal resistance. We don't have to worry about internal resistance in this question. Yay! Now the capacitor is initially uncharged. The time constant of the circuit is 100 seconds. What is the potential difference of the capacitor across the capacitor time t is equal to 200 seconds? Okay, well, if we look into a formula, we're going to the formula sheet, we're going to find a formula which looks like this. X is equal to x naught 1 minus e to the power of minus t over CR. Now this over here is the formula for the charging of a capacitor. So it could also be applied for charge, for example. However, that's why it's given the symbol x, because this formula could apply to a couple of different quantities. But in this case, we're just going to apply it to the voltage. So V is going to equal V naught 1 minus e to the minus t over CR, like so. Okay, well, in this case, what we're looking for is V. We have the EMF, this is the initial voltage across the resistor, to be 1.5 volts, so that's just 1.5 times 1 minus e to the power of minus t, so t is 200, like so, and the time constant, remember the time constant is CR, is this one over here, so this is going to equal 1.5 times 1 minus e to the power of minus 2. Okay, so if we plug those numbers into a scientific calculator, we're going to get approximately 1.296, which up to two significant figures is equal to 1.3 volts. So the correct answer is D. Moving on to question 10. So a charged particle moves in a circular path of radius 1.2 centimeters in a uniform magnetic field. And okay, so the radius is 1.2 centimeters. We have a different particle which has a mass m. So okay, so no, that particle has a mass m, charge q, and v. But then we also have another particle, and that one has a mass of 3m, charge of plus 2q, and the same speed. That moves in a path r. What is the value of r? Okay, well, in this case, what we need to remember is that for all of those problems, we always set equal the centripetal force. So F centripetal is going to equal the magnetic force. So let's call that F magnetic. Okay, so your centripetal force is equal to mv squared over the radius, which in this case is r, and I'm going to set that equal to qvb. Now what we can do is we can rearrange for r, so all I need to do is just really swap those two to rearrange for r, and we're going to get that mv squared divided by qvb is equal to r. Now we can also do a little bit of cancellations, so we don't really need that v at the top, and we don't need this v over there at the bottom. Okay, well, the particle in this case has a mass which is 3 times bigger, so that's times 3. It has twice the charge, and it has the same velocity. So if that's the case, the value of r is going to increase by that factor, which is 3 over 2. So if our radius was 1.2 centimeters, our new radius is not 1.5, 1.2 of course I meant to write. Our new radius will be 1.2 times 3 divided by 2. And this is equal to 1.8 centimeters. So the correct answer is C, 1.8. On to question 11 about percentage uncertainty. So we're given a formula for the acoustic impedance Z of a material, and we know that the percentage uncertainty in L is 1.2%, the percentage uncertainty in C is 1.8%. M has no percentage uncertainty, it's negligible. What is the percentage uncertainty in Z? Okay, so in this case we're multiplying and dividing quantities, so that means that we need to add the percentage uncertainties. So our percentage uncertainty in Z is going to equal the percentage uncertainty in I was going to write M, however the percentage certainty of M is negligible, so I'm not going to write that. So the percentage certainty in C plus the percentage uncertainty in L cubed. Okay, well, a good tip or good rule of thumb to remember is that anytime you have the percentage certainty of a quantity raised to a power, that is actually equal to the to 3 times the percentage uncertainty in that quantity. So the percentage certainty in L cubed is actually 3 times the percentage uncertainty in L. So that means that the percentage uncertainty in Z will just be your percentage uncertainty in C plus 3 times the percentage certainty in L. And that's really the catch of this question, so to speak. So your percentage uncertainty in C is 1.8% plus 3 times the percentage certainty in L, which is 1.2, so that's 4.8. Sorry, that's 3.6 plus 1.8, which is going to give us 5.4%. So the correct answer in this case is D. Question 12. The table shows some data on 2 tissues in a patient. So we've got some values for the acoustic impedance and the density. Now, if you remember, the acoustic impedance in general is equal to your density multiplied by the speed of sound in that particular substance through which the ultrasound is actually going. And if we look into our formula sheet, we're going to find a value for the or a formula for the reflected intensity. It's right at the end of the last page of your formula sheet, and it says over there that IR over I naught is equal to Z2 minus Z1 all over Z2 plus Z1, and this whole thing is squared. So this whole fraction is squared. Now it's asking us for the percentage of the ultrasound intensity reflected at the boundary. So your reflected intensity divided by your original intensity, well, if you just times that by 100, that's actually your percentage of the reflected intensity. So as long as we find this quantity, IR over I naught, we're in general in business with this question. So this is going to equal Z2 minus Z1. Now we're going into boundary 2, so this will be, our boundary 2 has an acoustic impedance of Z, so we can just say Z minus, the first one has an acoustic impedance of 1.5 Z, so 1.5 Z all over the same expression but add it together, so that's going to be Z plus 1.5 Z, and the whole expression is squared. Okay, well, what we can do is we can just factorize Z out of this equation, really. So at the top here we're going to have Z. Well, actually, let's just add those fractions together before actually factorizing. So it's going to be minus 0.5 Z all over 2.5 Z, and we can cancel the Z's out in a second as well. Just because I write this Z with a little line, just kind of used to it this way, I'm just going to cross it out with a different color pen just to make this a little bit more noticeable. Okay, so we almost have a value for IR over I naught. All we need to do is just write down that IR over I naught is equal to minus 0.5 all over 2.5 squared. And if we put that into a scientific calculator, minus 0.5 over 2.5 and we square it, I'm going to get 0.04. Now it's not yet a percentage, so what we need to do is we need to times that by 100, so this will obviously be equal to 4%. So the correct answer in this case is B, 4%. Question 13. We're almost there, guys. Just a couple more questions to go. So an electron is released at a distance r from the surface of a positively charged sphere. It is attracted towards the center of the sphere, and it moves until it touches the sphere. So we have an electron over here pulled by force F, and this moves towards it, hitting the charged sphere. Which of the following statements are correct? Okay, so the first one, the area under the F against R graph is equal to the work done on the electron. Yeah, this is correct. The reason for that is because well, work done in general is the area underneath a force against R or distance graph. So no matter what the shape is, you know, it could be something like that. It's the area under the curve. For those of you guys who really enjoy mathematics, you don't need to know this for the exam, but work done really is the integral of the dot product between the force and the dr vector, or the integral of f with respect to r. Anyways, back to the question. The electric field E at a distance r is equal to F over 1.6 times 10 to the power minus 19. Well, in general, electric field is equal to F over Q. In this case, the charge is an electron, so that's correct. That's a correct statement. 3. The work done on the electron is equal to F times R. Now, that's not the case. It's equal to the area, so 1 and 3 cannot be correct simultaneously. The reason why 3 is not correct is because this force changes. So it's not a constant force. Changes when the electron moves. So as soon as F sort of is, let's say the electron comes here, the magnitude of the force will actually increase, and will increase quite substantially. So changes when the electron moves, like so. Remember, the closer you are, the bigger the force on the electron. So in this case, the correct answer will be only 1 and 2, so that'll be B. So the correct answer is B. Okay guys, question 14. Which lepton is emitted in the decay of an up quark and is affected by a magnetic field? Well, looking at those answers, the neutrino is not affected by a magnetic field, and so is the antineutrino. So it's not going to be A or D. Those guys have a charge of 0, so they're not going to be affected. Now, is it the electron or is it the positron? What we need to remember is our beta plus decay equation, in which a proton is going to turn into a neutron. Now, when that happens, charge needs to be conserved. On the left-hand side here, the charge is plus 1e. However, the neutron has a charge of 0. So we're going to need something else to compensate for that reaction, and that is the positron, which has a charge of plus 1.6 times 10 to the power minus 19. We also get a neutrino over there, even though that's not important for this question. In this reaction, a proton, well, that's 2 ups and a down. That turns into a neutron, which is 2 downs and an up, plus the positron plus the neutrino. Now, in one of those reactions, one of those up quarks, let's say this one, the middle one, has turned into a down quark. So the correct answer is C, a positron. Just a little disclaimer that I've gone into quite a lot of detail. This is just for revision purposes and just to be as clear as possible in my explanations. You don't always, well, for this case, you only getting to the correct answer will give you the correct mark. So I encourage you to perhaps write a little bit less in general than I do, because when I do these videos, I just try to be a little bit extra clear and sacrifice speed but that's the opposite to what we should do in exams during multiple choice. Okay, and finally, question 15 on the topic of medical physics. A contrast material is used while taking an X-ray image of a patient. Which statement is correct? Iodine is a contrast material. Yes, that's true. In fact, it's one of the most popular contrast materials. Technetium is not a contrast material. It's used in the production of radioactive nuclide, which some of which can be injected into a patient for the purposes of medical imaging. Contrasting, so it's not this one. A contrast material must have a short lifetime. That's not necessarily true. And contrast material is used for acoustic matching. That's also not the case. Normally gel is being used for acoustic matching in ultrasound scans. So the correct answer here is A. Okay folks, so hopefully you've enjoyed going through these questions and have a look at my solutions. If you have enjoyed this video, please consider subscribing and liking this video. Thank you very much.